All right, hello everyone. Welcome to our latest episode of the data algorithms and tools of ISIE Lifecycle Sustainability Assessment Board. And today I have the pleasure to host our guest, my friend, and also the member of the LCSA board, Dr. Paul Wolfram. Paul has a PhD degree in industry ecology from Yale University. That's where we actually overlap for like the 3 years, I guess, almost, right? Like, yeah, time flies. And Paul is a research scientist at the Joint Global Change Research Institute, and which is kind of part of the PNNL, and he is the expert in life cycle assessment of fuel and the vehicles. And I believe today Paul's gonna bring us his recent research on comparing GCAM's outcome with the GREET's fuel life cycle estimates. So without further ado, the floor is yours, Paul.
Awesome. Yeah, thank you, Qingshe. Thanks for the invitation. Very glad to be here and talk about our recent work on comparing, basically using GCAM, which is a multi-system dynamics model or multi-sector dynamics model, using that as an LCA tool and comparing it with estimates from the GREET lifecycle assessment model. So the title is Do Multi-Sector Dynamics Models and Lifecycle Assessment Models Agree? Comparing GCAMs with GREET's fuel lifecycle estimates. And I didn't do this work by myself, obviously. So thanks to my colleagues, Paige and Nawaf. Let's get started. I want to start with a little bit I want to start with a background on the overarching project. So where is this work really coming from? This work that I'm presenting here is part of a big project. It was sponsored, it is sponsored by ARPA-E, which is an agency of the US Department of Energy. And this agency is focused on funding novel and promising energy technologies. We had a few project partners. All of those project partners were tackling different tasks. I think for here would be good to use the laser pointer. Yeah, so for example, we are working with the American Bureau of Shipping. They are really focused on the maritime freight modeling part. And then other partners, they have specific models for just railroad and trucking. And basically where we come in GCAM, we provide prices and emission estimates and energy use estimates for different fuels. And then in this part, this all gets integrated into an intermodal route planning tool. And at this point, I should probably explain what intermodal means. Intermodal basically just means the transportation of goods, for example, in containers. But those containers within one single journey, they might switch between different transport modes. So, for example, one container might start its journey on a train, then gets loaded onto a ship, and it's exported to a different country, for example, where it is then delivered to its final destination in a truck. So just combining those different modes is usually what's referred to as intermodal. And the overarching goal of the entire project is to model a pathway for the US freight transport sector in which 60% of greenhouse gas emissions reduction is achieved by the year 2050, with no more than 20% increase in costs. And so the focus is both on switching fuels, but also switching and combining different freight modes. And so this is the background of the overarching project. And part of this project was to validate GCAM. And we did that by validating our GCAM results. As I said, we provided fuel costs and emissions and energy requirements. We decided to validate that against estimates from the 𝗏𝗂𝗪 life cycle assessment model. So yeah, that brings us to one of the most important questions of this project. How can we actually connect the two different model families, and how do they relate to each other? On the one hand, we have life cycle assessment models like 𝗏𝗪𝗪. 𝗏𝗪𝗪 is focused on vehicles. That's why I'm showing this example here. Those life cycle assessment models, they are more detailed. They have a better consideration of physical characteristics, such as, it really goes down to the component level of different vehicles. What is the size of the battery, and so on. And of course, in multi-sector dynamics models, that's all of those vehicles are modeled in a more aggregated way. But as the trade-off is that multi-sector dynamic models like GCAM, they are more holistic, more systemic. They include interactions with all the other sectors. So they include transport, industry, refining, the power sector, and even some simplified climate models. For example, GCAM makes use of the Hector simplified climate model. So there is a challenge between those two opposites, but there's also, of course, an opportunity. By combining those two families, we might get additional insights and more actionable insights. And so to dive a little bit deeper into what life cycle assessment is, or I actually won't talk much about life cycle assessment because I'm pretty sure everybody on this call is pretty knowledgeable about that, but I want to briefly just talk specifically about the 𝗏𝗪𝗪 life cycle assessment model. It stands for, I have it written down here, it stands for Greenhouse Gases, Regulated Emissions, and Energy Use in Technologies. And it's developed and maintained by the Argonne National Laboratory. This chart here is basically coming straight from their website. And the 𝗏𝗪𝗪 model is basically two models. One is for the energy cycle, 𝗏𝗪-1, and this tracks basically the fuels or the energy carriers, hydrogen, electricity. All of those fuels can be assessed on a life cycle basis from extraction to fuel use with the 𝗏𝗪-1 model. And then 𝗏𝗪-2 captures the vehicle production cycle, all the way from raw material mining to vehicle use and then recycling or decommissioning of vehicles. That part is included in 𝗏𝗪-2. Here for this work, to make it more comparable, we only use 𝗏𝗪-1. So we are basically doing a well-to-wheel analysis. We are only providing the transportation fuels. And GCAM doesn't really have much information on the vehicle production cycle. So for a better comparison, we're focusing on the energy cycle. On the other hand, multi-system dynamics models like GCAM, those are highly nonlinear models. GCAM specifically includes 32 global regions, whereas GREED is focused only on the US. Yeah, GCAM can make projections all the way to the 2050 or even 2100 timeframe. There is also a GCAM USA version, which we did not use here, but it provides estimates for all the 52 US states. There is a public repository for GCAM. You can find that here. And maybe a little bit more general, we can, in GCAM, we can run those if-then scenarios. We have different exogenous assumptions like population, labor productivity, different assumptions on various technologies. That includes different fuel pathways that I will talk about. We can also assume different policy measures. Yeah, and then the model itself includes the energy side of things, as I mentioned, climate models, but also a water module, agriculture. So it's a very complex model. And output, of course, include economy-wide greenhouse gas emissions, taxes, prices of different goods and commodities, and so on. I think you get a picture here. And so I want to delve a little bit deeper into how specifically we used GCAM for this work. So we started by running 288 scenarios defined by permutations of the key uncertainties shown here. We have different variables shown here, and those are what made up those scenarios, or specifically the permutations of those scenarios. So for example, from each area, like H1 through H4, R1 through R3, and so on, you can pick one permutation, and that basically then yields one scenario. So for example, H1, R1, B1, N1, C1, P1 is our reference scenario, and what it includes is default hydrogen and ammonia production. So that in our case means that hydrogen and ammonia are produced from natural gas. We have other scenarios where we assume that those energy carriers are produced from green electrolysis, either at default cost or more advanced cost. We also have a blue hydrogen assumption, which means hydrogen is produced from natural gas with CCS. And similarly, we have different assumptions for renewable electricity, advanced cost. We can constrain renewable electricity to a certain amount. Same with biomass supply, nuclear electricity, CO2 storage, and the stringency of the global policies assumed. Either no policy, 50% global greenhouse gas reduction by 2050, or even a net zero scenario by 2050. Oh yeah, and I should mention, we also ran 12 additional scenarios just for land use change emissions from biofuel consumption, because those land use change emissions, at least in GCAM, tend to result in fairly big contributions to the life cycle assessment, total greenhouse gas emission factors. Here's a hopefully a fairly intuitive chart how we implemented this algorithm that basically swims upstream in GCAM, starting from a final fuel, like here in this case, ammonia energy, and then it basically swims upstream through the supply chain, through all those sectors here, all the way back to the primary energy inputs in GCAM, of which we have 9, and those are coal, oil, gas, nuclear, biomass, geothermal, solar, and wind. And this example just shows ammonia, but this is how we have the same process for all the different 9 fuel pathways we have assessed so far in GCAM. So then I want to start talking about some of the results. You can see here in this chart the 9 different fuel pathways I was mentioning. We have ammonia, e-diesel, electricity, Fischer-Tropsch biofuels, Fischer-Tropsch biofuels with CCS, so carbon capture and storage, hydrogen, liquefied natural gas, petroleum diesel or conventional diesel, and renewable diesel. And what you can see here, these are the life cycle assessment based emissions factors, grams of CO2 equivalent per kilowatt hour. We will see in the next chart, I believe, which greenhouse gases are included here. But let me start here by saying this is the unique advantage of GCAM or LC-GCAM, that we can look at the greenhouse gas emission factors over time. So in this case, from 2030 through 2050. And I've highlighted, so you can see here, I plotted all 300 scenarios. And maybe just for better visibility, I highlighted 3 different scenarios. And I'm not showing here the cryptic code H1R1 or whatever. I'm just going to say that the red line is the reference scenario. So here we use all the default assumptions. So like I said, for example, for hydrogen, that includes that hydrogen is being produced from natural gas. And then we have I highlighted 2 other scenarios that use different combinations of assumptions. And I believe the green one, for example, here uses the net zero policy setting. So that's the most ambitious scenario. And for most fuel pathways, the blue scenario is kind of somewhere in between. So what else do we see here? Well, first of all, obviously, when ammonia and hydrogen are produced from natural gas, they actually don't lead to much of a greenhouse gas emission reduction. We can see for comparison, this black dotted line here is petroleum diesel. That's the carbon intensity of petroleum diesel. And ammonia and hydrogen are pretty similar here. And with the current assumed grid in the US, where electricity comes to a big part still from natural gas, even e-diesel and electricity actually don't look that favorable. But when you switch to renewable electricity, like we assumed here, then you can clearly see a big greenhouse gas mitigation potential for e-diesel, electricity, Also hydrogen, ammonia as well. Something else that we can see is that 𝗪𝗪 or generally biofuels, they don't show that much difference over time. They're fairly linear. And that's because our assumptions just don't change the impact much, the results that we see. So for example, whether hydrogen or electricity are produced with green electricity doesn't matter that much for biofuels because there's not much electricity or hydrogen input into those fuels. What matters more are the different land use change assumptions. Those have quite an impact on those fuels here. And similarly, in GCAM, we don't have many mitigation levers for conventional fuels like LNG or petroleum diesel. So those fuels are basically flat over time in all scenarios. Okay, then moving on to the second results slide, which shows the comparison between the GCAM results and the GREET results. Same fuel pathways here, those 9 fuels. This time I'm only showing results for 2030 timeframe, again for the US region. And in solid bars on the left side, we can see GCAM results. And the dotted bars on the right side, those are GREET results. And overall, what we can see, if we look at the black dots, those show us the totals or the net totals. We generally have a pretty good agreement between GCAM and GREET. So for example, here, for ammonia, we find that the error between the two models is less than 10%. Maybe except for LNG here, you can see LNG in the GCAM model is quite a bit bigger. I think the total difference is 13% here. And that's because in GCAM, well, we assume that LNG is mainly for maritime purposes, so for shipping. And so we include, what's that called again? We include more methane emissions, for example, from methane engine slippage. So LNG tankers have shown to have quite a little bit of slippage of methane during the ship operation. And that's not necessarily included in the GREET model. Oh yeah, and that also brings us to this point here, which greenhouse gases are included. We have methane at this point, carbon dioxide and nitrous oxide, and also hydrogen. Hydrogen has been shown to have an indirect impact on basically on the lifetime and the forcing of other emissions or emission components in the atmosphere, and it can therefore be assigned an indirect greenhouse gas impact. We can see that here in the hydrogen pathway. There is a small contribution from hydrogen. Moving on, I also want to talk about those little errors that we can see here for some of the fuels. And that meant that we had to do some harmonization of input assumptions between GCAM and GREET. And we started with electricity. This is the default result. of electricity emissions in the US from GREET. But GREET assumes a very different electricity mix in 2030. GREET is much more optimistic about renewable energy deployed by 2030. And yeah, so we just wanted to harmonize that. So we basically took the electricity mix from JGCAM, plugged that into the GREET model. So we harmonized how much natural gas we expect in 2030 versus how much renewables versus how much coal and so on. And that gave us a pretty good agreement. And we went further and actually also harmonized the natural gas generator type, which actually resulted in a little bit less good agreement, but still very reasonable. And so, yeah, we did basically the same thing for other fuels. For e-diesel, we just had to align the assumptions about how much purchased hydrogen versus how much purchased electricity goes directly into the fuel production process, and harmonizing that led to really good agreement in the case of e-diesel. Because there is such big variation regarding land use change emissions, which are part of the blue bars here, we decided that, yeah, for this comparison, we leave them out. And once we leave land use change emissions out, the agreement between JGCAM and GREET is actually very, very good, within a few percentage points. But I'm acknowledging that here, if we include land use change emissions, and those are very high in JGCAM and very low in GREET, then yeah, we have quite a disagreement. What else? This is just a small change, but GREET essentially gives credits. And I'm actually forgetting the details, but I can, if you want to read about it, about all those details here, I'm happy to send along the manuscript, which is under review right now. I want to just show you this real quick. We did the same, not just for the emissions factors, but also for energy use factors. So that means how much energy was used in producing the fuel versus how much energy does the fuel provide. Generally, that is above 1, because you use at least as much energy to provide 1 unit of energy. But more commonly, we see those energy factors around 2. So that means you need twice as much energy to produce the fuel than what you get out of it. However, for e-diesel, you even need 4 times as much fuel. I believe that's the most inefficient pathway. LNG and petroleum diesel are actually fairly efficient. And again, we did some harmonization here as well between those 2 fuels. And yeah, that was my final results slide. You can head over to GitHub. We have all of this open access in some GitHub repositories. You can go to this JGCAM LCA repository if you want to reproduce the results of this paper. And you can also go to the JGCAM freight fuels repository if you want to check out the specific GCAM branch that we used and developed. And once you have that, you can modify assumptions for the specific fuel pathways, or any assumptions that are being made in GCAM. You can assess additional fuel pathways. You can assess the life cycle implications in sectors other than the US freight sector, and you can run additional scenarios and so on. And both my colleague Paige and me, we are more than happy to lend a hand if you're interested in this type of work. Maybe you're a PhD student and you're looking for an interesting project. This might fit the bill for you. And I'm going to wrap up here with a summary and a very brief discussion. What we saw is that we generally have pretty good agreement between GCAM and GREET for most of the fuel pathways. We were within a 10% error in terms of greenhouse gas emission factors and energy requirements. This work basically serves as a validation of GCAM as a fuel LCA tool or well-to-wheel analysis tool, at least for climate change impacts. We are not at the point yet where we can assess other impacts. In the literature, there are many efforts to perform LCA on top of IAM or multi-sector dynamic model scenarios. The advantage of our approach here is that we assess the climate impacts of several fuels directly, straight out of GCAM, without a need for a separate LCA database and model. And oftentimes, IAMs are being critiqued for being too aggregated. I mean, we saw it on an earlier slide. Technologies are not modeled in the same detail as LCA models are able to do. But here, one nice thing is that we can see that at least the total emission coefficient and energy requirements are in pretty good agreement with more detailed models. In some cases, we found GCAM to be, well, maybe I shouldn't use this word comprehensive, but yeah, we do include, let's just say there are differences in terms of, for example, engine slip for LNG and land use change emissions for biofuels. One important note is, though, we have to acknowledge that GCAM currently does not trace across regional boundaries. And our results will be more accurate for regions with limited energy trade. So for example, if a region exports or imports a lot of the fuel or a lot of the inputs to the fuel, then those might not be traced by LC-GCAM and therefore lead to too low or too high estimates. But for our US example, the tool worked pretty well. And so, of course, this could be another potential area for improvement in the future. And I think with that, I'm coming to the end. I wanted to say thank you mainly for ARPA-E for sponsoring this project and for discussions with many other people, bright people. And yeah, with that, if there are any questions, I would be happy to hear them and try to answer them.
Thank you very much, Paul. I think it's a very comprehensive analysis, like all of your previous studies, I think. Yeah. I do have a few questions, actually. So one thing 'cause based on my experience with GREET is the GREET-1 fuel cycle model, right? So it does have fixed technology assumption plus a land use change from a certain scenario that's based on GTAP model, right? And then in GCAM, you have your
Yeah.
own scenario and like
I think
sectoral
you meant GTAP, right?
GTAP, yes.
Yep.
Yeah. And then for GCAM, you have your own kind of market dynamics over the years. So um, this means the change of the let's say the technology mix, the assumptions are different. So that's why you did harmonization at the end. I just want to kind of clarify that, right? So you have one slide showing that after you harmonize the electricity grid, like a natural gas generator type,
Mhm.
you will have sometimes more like a closer results. Yeah.
Yep.
Okay. Yeah, because I think to me, that's the hardest part
Mhm.
to do it, right? So every model has their own assumptions, and
Yep.
then and and then maybe I can ask you to reiterate the benefit of basically having this internal carbon counting capability in GCAM compared to, for example, I just ran GREET, and
Mm.
then I will see different numbers, right? So, um, like, what is the benefit of not running them separately, I guess?
Okay. So yeah, you mentioned a couple of things. You're right. Greed has its land use change emissions based on 𝗂𝗪.
Yep.
𝗂𝗪 is also an Excel spreadsheet model that you can link to Greed. And 𝗂𝗪 is a calculator just for land use change emissions for different biofuels. And for that model, I think it's also maintained by Argonne National Laboratory.
Mm-hmm.
They use GTAP estimates, and those GTAP estimates basically it works in a similar way that GCAM works. And I'm I'm I only have a very superficial understanding, but the way I understand it is you basically shock the model. You introduce a very large demand shock for biofuels,
Mm.
and then you analyze how much more emissions that brings about. And yeah, basically, then you assign those emissions to one additional or one marginal unit of biofuel, and that's how you get to your land use change emission result. And I believe GTAP and GCAM work in a similar way in that regard, but still the final results are pretty different. And I myself would have to dive deeper to really understand where those differences come from.
Yep. You probably won't get discussion from the reviewers. You said your
Oh yeah,
manuscript is under
yeah,
right? Yeah.
yeah, that's fair. Um, what else? You also asked what's the advantage of our tool? So, well, one thing is if you use Greed
Mm-hmm.
as a standalone tool, you don't capture all the market dynamics, right? You don't have an endogenous electricity mix or fuel production, all the dynamics that GCAM can capture are all exogenous assumptions in Greed.
Yeah.
And then as I mentioned, there has been a lot of effort in the literature to combine life cycle assessment databases like 𝗂𝗪
Mm-hmm.
with databases of scenarios that come from integrated assessment models or multi-sector dynamic models. But there's a lot of labor and a lot of time involved in just constructing those databases and models. And here we provide a script, a code that is fairly short, and it's open access, and it's uploaded to our GitHub repository. And like I said, it swims through the GCAM database in a pretty efficient manner, and then calculates the life cycle emission factors. But like I said, at this point, it's only for greenhouse gas emissions and for a limited number of fuel pathways. And there could be problems with regions that have a lot of exports and imports. But for our study here and for the US region, we got pretty good agreement with GREET.
Yeah. Oh, thank you very much for the details, Paul. I think, yeah, so basically endogenize those market dynamics into the basically LC or carbon accounting assumptions about, background electricity grid, some other like technology changes are very important. Yeah, as you mentioned, I remember, yeah, I think probably since 2020, people start to really kind of increase the technology representativeness and the resolution in IMs, right? So like you want to have, more, technology explicit MFA model integrated with IM and the like for example, LC model that connect to the future electricity grid and all these things. Yeah, I think this is a very exciting trend, and we hopefully get a more integrated model with integrated assessment model. It's like double integration. Yeah. Yeah. All right. Yeah. Sorry. Go ahead.
Yeah. No. I share your excitement. I think combining LCA and IM has a big potential to find, to get some actionable insights and to see some interesting results.
That's great. So probably can you flash the last slide where you have the GitHub repo and everything before we actually end this recording? So
okay,
I can just see it.
Sounds good.
All right, great. Thank you again, Paul. It's always a pleasure to talk with you, and
likewise.
Yeah. Hopefully we're gonna meet in person very soon.
Yes, agreed.
Yeah.
Thank you so much.
Yeah.
Have a good rest of your day.
Yeah, you too.